Okay, so for this equation, we're going to do the opposite of what we did before. We're going to actually show that it's not exact, but then do a fix so that it becomes exact, and then we can solve it. So just like before, we had our capital M, and again, that's the coefficient on dx. And then we have our capital N, which is the coefficient on dy. And again, we're taking partial derivatives, and they're mixed. So we're taking the m sub y, which is going to be 2y minus x. And then we're taking the n sub x, which is just 2x. And quickly you notice that these two partial derivatives are not equal, so the equation itself is not exact. Now, oftentimes, you can take what is called an integrating factor and multiply the equation by the integrating factor to make the equation become exact. And then you can solve it like you normally do. So let's go through now and multiply this 1 over x times y squared times our differential equation, which is y squared minus xy dx plus x squared dy. And again, we're multiplying on both sides, so that's times, of course, the 0 that's already there. So now, of course, when we distribute, we're going to have a 1 over x, and then we're going to have a minus 1 over y. And again, that's the dx coefficient. And then we're going to multiply and distribute again. So now we're going to have a 1, actually just x over y squared. So x over y squared times dy. And of course, 0 times anything remains 0. So now we have a brand new capital M. And we have a brand new capital N. And we want to check for exactness this time around. So once again, we take m sub y. This time around, m sub y is going to have 0 for the first term. And then it's going to be plus 1 over y squared for the second term. That's using the power rule. That's already a y to the negative 1. Subtracting 1 makes it y to the negative 2 and changes the sign. And then n sub x is equal to 1 over y squared. You notice that these two partials are now equal to each other. And so the new equation is exact. In the next video, we'll actually go through and now take this equation and solve it to get a solution to the original differential equation.